With that, we'll continue on this afternoon with Bonnie James, who's the Program Executive for the Technology Demonstration Missions Program. Bonnie?
Well, first, let me say right away, sorry. You got to hear Jean-Francois' beautiful, beautiful accent and LK's beautiful accent, and now you're stuck with my southern twang. So I am so sorry. Let me just tell you that right up front. I'm Bonnie James. For those folks I haven't met yet, I hope to meet each of you soon. And it's my privilege today to talk to you about an exciting new program in the Office of the Chief Technologist, the Technology Demonstration Missions Program. And that program will be also led out of the Marshall Space Flight Center. And Susan Turner is the point of contact at Marshall. Susan's right there. And she and I will be leading the breakout session tomorrow. So if there's questions or you need further detail on anything that you see here today, we can talk about that tomorrow as well. Okay, the Technology Demonstration Missions Program is one of 3 programs in the Capability Demos area. And as LK so eloquently said, we fly things. That's exciting. So why have a demos program at all in a space technology development effort? Why is that important? It's expensive to fly things, so why have that? Well, one of the greatest challenges that we face in incorporating advanced technologies into actual missions is this gap, and bridging this gap between early stage ground development and the actual mission use. And that's why the primary objective of this new program is to do that, to bridge that gap by maturing space technologies through flight qualification and demonstration into mission infusion. So those are 2 primary focal points for this new program, and that's space flight qualification and mission infusion. Let's look at a couple examples of why that's important, why space demonstration is important at all. If you look at ion propulsion technology and just look at the historical record of ion propulsion, you can trace back to 1906 when Robert Goddard first theorizes about ion propulsion. And he performs some first initial experiments with ion thrusters at Clark University in 1916. And then in the 50s, you see NASA building ion thrusters in the laboratory. And if you trace back, you'll see many different tests, a lot of literature about laboratory experimentation of ion thrusters in the 60s and in the 70s, in the 80s and the 90s. But you have to fast forward to 1998 to the NASA New Millennium Program and their Deep Space One mission, which launched in 1998. And the New Millennium Program, NMP, was also focused on demonstrating new advanced space technologies. So DS-1 was their first flight, and it was the first flight demo for ion thrusters. And it worked beautifully. It worked very successfully. Then what do we see happen in history? We see in 2001, NASA approves a discovery mission that will utilize ion propulsion, Dawn. It's a mission to the asteroids. And we see Dawn launching successfully in 2007. So if you look at the time frame on the chart, just stand back and look at the historical record, you can see that we've been working ion thrusters since the early 1900s. And we went a century working those ion thrusters. But as soon as we had a successful flight demo, then ion propulsion was available to all of us. Let's look at another example, aerobraking. Aerobraking uses the atmosphere, the natural resource of the destination, to change orbits in lieu of propulsive fuel. You can trace back to the 40s when science fiction writers referenced aerobrake. And you can find plenty of technical references for aerobrake in the 50s, and in the 60s, and in the 70s, and in the 80s. You can find traces back to the German rocket scientist team where they were proposing aerobrake at Mars. But then you have to fast forward to 1993 to find the Magellan mission to Venus. And the Magellan mission was a science mission to Venus, mapping the gravitational field. And at the end of that mission, the spacecraft was left in an elliptical orbit. And they decided to go ahead and flight demonstrate aerobraking, see if that would work in the Venus atmosphere. And it worked beautifully. In fact, if you go back and look at those write-ups, you'll see that that aerobraking technology actually allowed for a whole second mission at Venus. And the spacecraft was out of fuel at that point, so aerobraking was their only option to continue. And it worked beautifully. So then what do we see? We see right away NASA decides they're going to baseline aerobraking into the Mars Global Surveyor mission. And that was 94. So we see aerobraking in the 40s, the 50s, the 60s, the 70s, the 80s. In 1993, we have a flight demonstration. In 94, we're using it, and we've been using it ever since, very successfully. So those are just two examples of why flight demonstration is so powerful and so important to us, because it allows us to infuse that technology. I wanted to share some key elements of this particular demonstration program, because some of these elements are similar to other flight programs that you've seen in the past, but some of them are really unique to this new program. And again, tomorrow we can talk about these in greater detail in the breakout, but I did want to share some of this for you today. Cross-cutting. For this particular program, the technologies that we're going to demonstrate need to be cross-cutting, and we define that as a technology with the potential to benefit multiple customers. Systems level. We're looking for system-level demonstrators, not component level. We're looking for brand new capabilities like ion propulsion or aerobraking. Technology readiness. These technologies need to be mature. They need to be ready for demonstration. And the proposed demonstration needs to take that technology and make it ready for first mission use. The project life cycle, we're looking at a 3-year effort. And I know I've talked to some of you in the hallway at break about this, and that's a fairly quick turnaround. And that was intentional, because we want to move these technologies through, get them demonstrated and infused. And we can talk about that more tomorrow in the breakout session as well. Life cycle costs, we're looking at a typical project cost of about $150 million. And that funding includes all elements of that flight test. The planning, the hardware and software development, the launch costs are included in that, the ground operations and post-test analyses. And cost sharing is also a very integral part of this new program. To demonstrate a potential infusion path, the teams are going to be required to have a sponsor or multiple sponsors to help cost share the demo. And a minimum of 1/4 of the total cost must be contributed by some party outside the Office of Chief Technologist. So let's talk about opportunities for you to participate. We're anticipating yearly calls for system-level demonstrators. That's our goal, as funding will allow. The goal is to have several proposals selected each year. We'd really like to have 2, 3, 4 ongoing projects in the queue each year. Open competition is very important to us. As Bobby has mentioned, we want to cast the net widely. We want all of your brilliant ideas. And so the competition is open to NASA, other government agencies, academia, industry, and international partners. And we understand that there are some barriers that might hold back some of your participation, such as intellectual property rights and data rights, and we're working that. We're working that now with NASA Legal, and we'll continue to work that because we want this to be as flexible as possible and we want as many of you to participate as possible. So the approach is going to be request for information, RFI, followed by request for proposals, RFPs. And the RFP approach that we're considering is the BAA. So let's talk just a minute about the RFI. Because we did release an RFI for technology demonstration missions on May 27th, and that closed at the end of June. And we were really pleased to get over 200 responses to that, and we are still digesting and collating all of that information. And we're loading your information into a database that we can utilize for the BAA in the future. We saw with this RFI very broad participation. We got responses from NASA, but other government agencies, organizations as well, industry, academia. And then if you look at the capabilities represented, it's very, very broad, broader than we even anticipated. And I think I mentioned in the RFI, and I want to reiterate today, that those RFI responses are going to be used to formulate the BAA. And some of you have asked me about that, and we can talk more about how we're going to utilize that information tomorrow at the breakout. So let's talk just a minute about the BAA. We're anticipating a two-step proposal process. Step one is the screening proposal, and 10 pages or less, and that's to help you and to help us. The step one proposal should include proof that this technology really is cross-cutting. Your preferred carrier, we'd like to have that information in this 10-page or less step one. We really want to be aggressive in understanding what launch providers are needed and going after those for you folks. We're going to need a ROM cost, a rough order of magnitude, and some information on who your cost-sharing source will be. And we're anticipating 2 months to formulate this step one and prepare that submit. And OCT will be preparing a review team to review those proposals, and that review team will determine which of your proposals will then move to step two. So step two is a full flight demonstration proposal, 50 pages or less, very typical for NASA flight demonstration proposals. 3 months for that proposal prep and submit. And we're going to use the same review panelists as we did in step one because they're familiar with your proposal, your concept. And the final selection official will be the NASA Chief Technologist. The BAA release, we're currently targeting for October 1. If funds are available, we can be ready before then. So with that then, I hope you're just as energized as I am about this new program and all the possibilities that it brings. I'm excited about the new capabilities that a tech demo program can bring to us because we've seen what tech demos can do in the past. Just like Deep Space One allowed us to utilize ion propulsion and Magellan allowed us to now utilize aerobraking. The possibilities are endless for this program. I'm very excited about that. I think we're really talking about brand new advanced capabilities coming into the aerospace community, and that's pretty exciting. And I really feel like they can change the way that we investigate, and they can really be changers in how we explore. Thank you. Questions?
I'm David Gump with Astrobotic Technology in Carnegie Mellon. If there's a continuing resolution as of October 1st, does that prevent you from going forward, or does your program not get halted by a continuing resolution?
I see Dr. Braun standing up, and I know he's dying to answer that question. I wouldn't want to take that away from you, Bobby, at all. So
dying is the key word.
True.
Thank you.
You're welcome.
Yes. So if there's a continuing resolution, there are a number of scenarios. First of all, many of the programs, not this one, but many of the programs that in fact, the innovative partnership programs that were in place in FY10 would be part of any continuing resolution, in terms of the funding, carry forward funding for FY11. In terms of the new program content, which, as I said, is about 60% of the budget for space technology in FY11, it depends on specifically what Congress does with the continuing resolution. There are approaches where Congress can authorize some of these activities, all of these activities, or none of these new activities. And that is something that is playing out, frankly, this month and next month. And we'll know at that time. Where we are today, just to be clear, where we are today is Congress is in the middle of that discussion. All the markups are not complete. I think when the markups are complete, I think we'll have a much better understanding of congressional intent, and NASA plans to, abide by the congressional intent. Okay.
Thank you, Bobby.
Dave Chenette, Lockheed Martin. Does the 25% external contribution mean that the total program can be $200 million or more, depending on the external contributions, or that the OCT part is 115 or less?
The typical cost for the check we write is about $150 million, but the contribution from our partner can be whatever you can afford, as long as it's 25% or more of the total life cycle cost. Anything you want to add to that? Any other questions? I think for the RFI, I probably fielded 5 to 10 questions a day, I would say, on the telephone or email. And I would say about 90% of those questions were about this partnership and how do we deal with this exchange of monies. And something we're going to have to work through, and we can talk more about that at the breakout session, because I know that's kind of new. Thank you.